Okay, so let's say we were supposed to find the LU-Factorization of a given matrix, and we can either make the reduced matrix an upper or lower triangular matrix. Let's go with let's go with an upper triangular matrix U, since it's going to be the row operations will be a lot easier. So in order to do that, we got to get rid of the 2 in the bottom left of the matrix. And we're going to multiply row 1 by -2, add it to row 3, and bring the change to row 3. Therefore, rows 1 and 2 will be the same. And our third row is going to be 0, -4, 2. And our operation is going to look like this. Now, what does this mean for our elementary matrix? You're just grabbing the same operation you did and you're going to apply it to an identity matrix. And that will be your elementary matrix. So, therefore, this will be our third row. And rows 1 and 2 will be the same. Now, we just have to get rid of that -4 in the third row. To do that, we'll just multiply the second row by +4, and add to row 3. So therefore, rows 1 and 2 should be the same. And we should be able to get that one last 0. Yep. What does the row operation look like? It's going to look like this. And what does that look like for our elementary matrix? Oh, it's going to look like this. We added row 2 by 4. So the third row should have 0, 4, 1. With rows 1 and 2 staying the same. Okay, so since we have the elementary row operations and our elementary matrices right here, we can then solve for, well, we can actually just find the LU factorization of the matrix A. So we have 2 elementary matrices times A. So we have E2 times E1 times A, which is equal to U, the upper triangular matrix. And then we just have to solve for A, where we have A is equal to the inverse of the first elementary matrix, the inverse of the second elementary matrix times U. Now, to find the inverse of our elementary matrix, we have to find a way for this matrix specifically on how to get rid of the -2 such that it becomes the original identity matrix. Therefore, ISO 3 in this case would have to be, you would have to multiply the first row by 2 and move it to row 3 to get rid of the -2. And there you have it. We'll do the same thing. Oh, and by the way, this is also the inverse of the elementary matrix. And then for this matrix, we would have to multiply the second row by a certain coefficient to get rid of that 4. Can you guess what it is? That if you say that it's -4, you would be correct. Okay. So we have the inverse of our elementary matrices. Let's go ahead and plug them in. And while we're doing that, while we are plugging out elementary matrices, it's all a matter of matrix multiplication. And you guys are probably wondering, well, where is the U exactly? Well, Let's think about that for a second. Oh, here it is. Why isn't there a U? Oh, let's look over here. We already got it defined. U is this matrix. Well, it's the matrix with the 3 zeros in the bottom left corner. And because of that, it's all a matter of simple multiplication. Oh, there we go. What does multiply of two elementary matrices? And as a result, we are left with the lower triangular matrix L. And because we have U right here, the elementary matrix of A is equal to L times U is complete. So, because we have obtained the LU-Factorization of matrix A, we can actually apply this in a more general sense, where we can solve the system of n linear equations in n variables, ax equal b, efficiently in 2 steps. For one, we can write that y is equal to u times x, and solve where for L times y is equal to b for y. And we can also solve the upper triangular matrix times x equals y for x. And the column x is the solution of the original system, because a of x is equal to L u of x, which is equal to L times y, which is equal to b. The second step is just back substitution, since the matrix U is upper triangular. The first step is similar, with the exception that it starts at the top of the matrix, as L is the lower triangle. For this reason, the first step is often called forward substitution.